Okay, so we are live. Welcome, Frederick. This is the December 17th edition of the QuantUniversity AI School Guest Lecture Series. My name is Sri Krishnamurthy. As many of you know who've been attending the QuantUniversity Guest Lecture Series, we started the QuantUniversity Guest Lecture Series again in the fall, and we have had multiple lectures mostly focused on artificial intelligence, financial services, adoption, various innovations, and also active risk management, especially in the context of various models, especially if they're not hosted, and obviously generative AI, which is the hot topic of the day. So with that said, there has been a lot of advancements which has happened in the last year. I was telling Frederick just a minute ago that students are choosing generative AI for their projects, and obviously Bitcoin is hot again in the discussion. So there is a lot of interest in the fintech world on new innovations and use of AI and various other concepts to build new business practices, but also look at these technologies with a closer lens on what can be trusted and what should be still thought about as a skeptical aspect, and we have to do our due diligence to make sure that we adopt it for our use cases. So I'm going to do a quick intro and then hand over the stage to Frederick in a second. Let me share my screen. So Frederick, I think you can see my screen. Just a quick check.
Yes, I can see your screen here.
Perfect. So for people who don't know me, my name is Sri Krishnamurthy. I started QuantUniversity in 2023. So it's been 11 years. We've been primarily focused on frontier areas with the intersection of machine learning, data science, and financial services. This is something which is close and near and dear to my heart. 20 plus years ago, when I started my career, I primarily was focused on distributed systems and agent-based computing, which obviously wasn't the topic of the day. And when I went into financial services, it was more of automation and thinking about leveraging various best practices to automate, reduce the amount of friction which happened in various processes. And 20 years later, so we are seeing all these innovations come up, and we are now thinking about how to leverage this to create new products and services and optimize various workflows. And in that realm, I've been teaching these topics for the past 10 plus years, both at QuantUniversity and also through the various programs I teach in at Northeastern University. So with that said, we have been making these educational materials available through the QuantUniversity channel, both on YouTube and also on the QuantUniversity website. And we have also been hosting these guest lecture series for the past 3 months. And we have been fortunate to have various professionals take their time from their busy schedules to present. And I'm so glad to have Frederick Shibboleth, who's been working on these areas for many, many decades now, and also is a highly respected faculty member at NYU. And he's going to be presenting today on alien intelligence, myth, and reality. Just to give you a little bit for the slate, if you want to jot down, next week, before we end the year, we're going to do a recap on all the things I've seen, teaching 5+ courses and supervising more than 25 AI-related projects at Northeastern University and at QuantUniversity through various customer channels. So we have put together what's called as a decalogue, which is like 10 steps to take your AI application from concept to production. I teach these semester-long courses wherein students start with nothing and then they end up with production quality AI applications over a period of 13 to 14 weeks. And we have standardized that into a framework. And I hope this discussion on December 23rd will help you kind of start your own prototypes and start your own AI projects in your companies. In addition, we are going to release what's called as an AI Canvas template, which I've developed over the last couple of years to enable people to start working on their AI projects. So that's going to be next week's final lecture for the year. And then we're going to kick off 2025 with a new certificate. So we call it the Generative AI in Finance Certificate, and it's primarily geared towards professionals who have been working on various AI, machine learning, and data science projects, and now want to actively integrate generative AI within their workflows. We've been primarily theming it for financial professionals because there are a lot of constraints on what you can and cannot do in financial services. And we have factored that in as we build the program. So we have both the components. One is the development component on what are available from plain old chat GPT kinds of applications to agentic architectures. By the way, agentic architectures are not super new. I mean, it's been there for plenty plus years. In fact, I wrote a paper on agent-based systems in 2002. But the intelligence aspect is the new thing, and the way we are leveraging agents is the new thing. So I'm going to talk about that in next week's session, but we're going to integrate those aspects as a part of this whole certificate program we're going to be launching. And then on January 20th, we are doing a live one-day course. It's going to be hybrid mode, both in Boston and also live streamed in ChatGPT, generative AI, and applications for financial professionals. If you're interested in any of these programs, please send us an email at info@qsandbox.com. So if you're registered to this webinar, we'll also be emailing you the details if you're interested in joining so that we can kick off 2025 and then be prepared for all the cool things which are going to come out. I'm just fascinated. I wish I was 25 years younger and still in grad school with all these technologies. There's so many opportunities to build new products and services. And the way we think about development, the way we think about acceleration, and we get this 10x value with leveraging all these technologies. It's just amazing the amount of innovation you could do leveraging these technologies. So hopefully it'll be a wonderful 2025 with all the innovations coming out. But we also want to factor all the things which we should be doing responsibly, factoring in all the policies, procedures, and regulatory initiatives to ensure that we are building a robust framework for whatever we build. So with that said, I'm going to hand over the stage to Frederick Chevrolet, who's been a collaborator, and I've known Frederick for many, many years now. We have met many times, and I really enjoyed discussing various aspects with him. So he has done his tour of duty at various consulting companies, at companies like Citigroup and EY. And also he has faculty positions at NYU, and he always is in the mode of learning. And in fact, he was one of the first few participants of the AI and machine learning risk management program we are offering in partnership with Premier. And he has provided a lot of feedback to improvise the program. And thank you, Frederick, for all your support and insights during the program. But he's also been creating all these new initiatives at NYU with new programs. And today he's going to be talking about his work on alien intelligence, myth, and reality, which is very timely considering all the drones which have been flying in the New Jersey, New York area. So I presume he has more insights on those, and he has integrated all those aspects as part of his presentations. If not, feel free to question him on any of these, and I'm pretty sure he has all the answers to all the unknowns and uncertainties we're seeing in today's day and age. With that said, I'm going to hand over the stage to you, Frederick. Welcome to the program, and please take it away.
Okay, well, it's very happy to be here today. Very honored to be on your program. Yes, I've known the program for many years. I think I met you when you started QuantUniversity, and or you were just at the very beginning, and I was part of one of the very first programs. So it's always been a pleasure to interact with you. So thank you for having me here. So we're going to speak about, can you see my screen?
Yes, I can see it now. Yeah.
Okay, I'm going to cut the video so that we have bandwidth to show the deck. So today we're going to talk about artificial intelligence, and we're going to talk about model size, model risk, and then I will speculate a little bit about the futures of AI based on the information that I've gathered with my colleagues and what I've heard at the most recent conference and things I hear from my clients. So we're going to start by going over what is intelligence and what are GPTs, generative pre-trained transformers. I talked very briefly about encoders, decoders. We'll do a little analogy with biology in terms of brain size and body mass. I found some interesting articles, and I think might be of interest to you. Then we're going to talk about the size of GPTs and how it has evolved over the years. And we're going to dive into what are different components of GPTs and how does this sizing account for the different modules inside GPTs. We're going to discuss training and performance and scale. And I'm going to show you that it looks like we've reached a little bit of asymptotic effect on the performance of LLMs in the last 1 or 2 years. We'll talk about superintelligence and the future of artificial intelligence. And then in conclusion, I'd like to dive a little bit into what's out there for us in terms of career change, in terms of professional opportunities, business opportunities, and where to look. Okay, so intelligence is a big topic. I would recommend this paper by François Chollet, as well as a very good book of Michael Noguer on financial services. Financial services and artificial intelligence, published at risk.net, which has like 100 pages of reference at the end. It's really impressive. So the LLMs, as we know them, okay, they are really what they're doing is giving the illusion of intelligence. That's why this anthropologist Yuval Noah, who published a couple of very interesting books on anthropology and these latest on artificial intelligence, calling alien intelligence. I like that term. So the questions, according to Chollet, is how well intelligence generalize. We have the level of no generalization at all, which is what I learned at school, how to build a program that works. So this example is tic-tac-toe. Okay, very, very deterministic. Then you have narrow scope generalization or local generalization, which makes inference based on what the system has learned. So it's essentially machine learning. So we call machine learning. So you train a model based on a large corpus of data, and you try to make some prediction based on a very narrow scope. Then you have a broader generalization, which is a large scope, but in a very narrow set of tasks. So the typical example is FSD, full self-driving. You teach a car to drive itself, and it's supposed to do that well and safely, but that's the only thing it can do. Then when we get to level 4, which is where humans stand, it's the case of extreme generalization. So at this level, human can perform tasks that have not experienced before, but they can conceptualize and use their previous learnings, their previous skills to perform that task. And then there is the 5th level, which is universal intelligence, which is things that are beyond human intelligence, like questions we don't even think about asking ourselves, but that superintelligence may be able or may go into. So we'll talk a little bit about superintelligence and how it applies to artificial intelligence in our case. So the question is, the finding of Chollet is how well do these artificial intelligence systems generalize? Really, that's what defined their level of intelligence. And so the next question that we could ask ourselves is, where do GPT stands for? So if you look at the rise of generative artificial intelligence, GPTs and LLMs in the recent past, in the last 5 years, you see that we have more and more parameters, and we're getting to a stage where we have a lot of models available. So you can go to that website. I gave you the link here. Really, they have different type of systems. So today we're going to focus on decoders, but you also have encoders. You have encoder decoders. You have many papers that explain the difference between the two. The decoder characterized by the attention mechanism, in particular what's called self-attention and cross-attention over the encoder outputs. So the idea is you prompt the system, and the system generates what's called a completion, which is a response to your prompt. And this is done in systems like GPTs, like Bloom, which is the basis for Bloomberg GPT. But you have also encoders that can be used for sentiment analysis, identity recognition, other applications, and the full sequence to sequence, which is used for translation, summation, Q&A. If you're interested in this one, there is a famous paper that was written in 2014 by Sutskever, who was until recently the head of research at OpenAI. So it's one of the foundation papers. It's 10 years old, but it's always interesting to read. Okay, so now if we look into what the nature has created, there is this interesting read on the evolution of large brain size in mammals. Okay, so if you take mammals and you do a linear regression over a log scale, okay, so the x-axis is body mass, and the y-axis is brain mass. And if you do a log scale, you have this big line here is the mammals. You have non-human primates, which is obviously above. And then here, with a much steeper slope, you have the hominids. So the hominids, they start really around 2.5 million years ago. To put things in perspective, that's 10 basis points less than 10 basis points of the existence of the Earth, which is we believe 4.5 billion years. The universe being about 14 billion years. So, it's really very recent, right? The rise of the hominids. So habilis was the one that could, start to use his hand. Then you have the Homo erectus. That's about 2 million years ago. Homo erectus stands up. Then you have the famous Neanderthalians. And more recently, the Homo sapiens, 300,000 years ago. So, we sit somewhere here. And the 700-gram ceiling is exceeded by the most advanced hominids and the elephants. But you see, the elephants do have a much smaller ratio on brain size to body size. So to give you an idea of the human brain, it's less than 100 billion neurons, 85 to 100 billion neurons. It's 100 trillion synapses, and the frequency of the response is around 100 hertz. So, how does this compare to GPTs? So here I take a number of popular generative pre-trained transformers. So it really starts in June 2018 with the paper, the Baswani paper. 2017 really is based on this paper. Potential is all you need. But the release of GPT-1 by OpenAI, June 2018. So the model has 100 and almost 120 million parameters. Okay, the important numbers are in red here. So that's a parameter size. The second important number is the size of the training data set. It's measured in tokens. The tokens, in English, a token is about a word. Okay, you have a bit more tokens than words, but you can approximate that for the purpose of this high-level presentation to a word. And then you have the context window. Context window is how many tokens can you put into your prompt. So here you see we start 7 years ago, essentially, with 6-7 years ago, 100 million parameters, until we get to GPT-3, which went to evolve into ChatGPT and became the first one that the general public started to pay attention, 175 billion. It's also the last one that is really well documented by the vendor, by the researchers. So we use that a little bit as a baseline. So GPT-3 has 175 billion parameters. It's trained on 500 billion tokens. And the context window is slightly over 2,000 tokens. And it's unimodal, it only handles text. Then we move into the famous GPT-4. GPT-4 is, so it's unclear exactly what the size of the parameters here. Some articles say it's 1 trillion, 1.5 trillion, close to 2 trillion. Well, it's much larger than GPT-3. The training data set is at least 10 trillion tokens, and the context window is 8,000 tokens. And it does text, but it does also some image. Then you have 4.0. So 4.0 is trained on 4 trillion. And then you start to see other vendors that emerge, in particular Google with Gemini 1.5, which is, I think, an excellent transformer. So 1.5 trillion tokens. And the claim of fame of Gemini 1.5 is a very large context window, okay, 2 million tokens. And it's multimodal. So here also, for the first 3 generations, it disclosed the number of layers and the number of heads. So heads is how you split your prompt when you start your inference in parallel streams, basically. And the layers is how many layers the attention mechanism go through to produce the output. So we went through to 12 times 12 to now 96 times 96 for GPT-3. And GPT-4 is probably larger, but we don't know the exact number. So diving into GPT-3, okay? GPT-3, again, is 175 billion parameters. What does that mean? Well, you really have, nine set of matrices, okay, 9 categories of matrices. In total, it's almost 28,000 matrices divided into 9 categories. So we'll go over this one quickly because it doesn't count. I mean, it counts for the processing, but it's very small compared to the rest. So we typically neglect it when we count for the number of parameters. So we start with the embedding vector. Okay, so we have 50,000 tokens, about 50,000 tokens, which are encoded. Each one of them is encoded into a vector of dimensional 12,000. It's at this level we have no context. Okay, when we do the prompt. So when we do the prompt, we're gonna essentially select a subset of all these 50,000 tokens, and that's the sentence that creates the question that we put into our context window, which for GPT-3 is up to, slightly more than 2,000 tokens. So now we have a prompt, we have our question. Then this goes into a combination with what's called the key matrix and the query matrix. So the key matrix is calling on the query matrix to create some context around the token, because there is no context, okay? And so that's going to be the first layer. Then you have what's called the value matrix, and then you have the perceptron. So the attention mechanism itself, okay, which gives the context to that token, which is embedded into a vector database, is split across 96 heads for GPT-3, So they're called attention heads. So they process the prompt in parallel. And they are layered together with perceptrons. Okay, so this is the attention mechanism, and this is the perceptron. So they're layered together, and there are 96 layers. So there, if you want, 96 iteration or sequence of processing by those layers, one after the other. So again, the attention layer is made up of a query and a key matrix, which is split across those 96 heads. So, if you multiply 96 by 128, you find 12,288. So what it does is it creates a link between the word and what's preceding the words. And there is this concept of masking when you are in a decoder, because you always want to move forward, meaning you don't want subsequent words to influence the word that you're going to find now. Okay, so it's always moving forward. You have other mechanism, neural network-based, encoder decoder. For example, when you do translation, you may want to look at the previous words as well as subsequent words to better understand the context. But if you're in a pure generative case, you mask the previous the influence of the possible words, posterior words compared to the previous word. So that's called masking. So this key matrix is calling on the query matrix to create essentially a softmax. Okay, so you multiply your embedded words by those two matrix, and then you normalize it by the sum of the exponent, and to create a softmax, which essentially gives you a probability distribution. Then you feed that into what's called a value matrix. So the value matrix is really 12,000 by 12,000, but to optimize in GPT-3, to optimize the size of those matrices, they do a low-rank decomposition. So, you really are going to have two matrices per attention head and per layer that are 128 times 12,000. So you apply those to the value, and it starts to create what's called the attentions. So it starts to put your tokens into some sort of context. Once you have that, so once you output from your first attention head, you move into your perceptron. So the perceptron is essentially a big neural network, which takes the dimension up to 49,000, which is 4 times the 12,000 of the embedding. And it's essentially a number of questions, and those questions have been learned at the training stage. And so it asks the questions to the previous layer, to the attention layer, and it produces an output. Okay, and that output goes on into the next attention layer, which feeds into the next perceptron layer, and it's adjusted by the bias. Okay, and you do that 96 times in terms of layer, and you do that in parallel 96 times. And at the end, you get an output, which is a probability distribution of tokens, and that gives you the completion, the terms, the response by the LLM to your prompt. So you can see the distribution of those parameters. The attention layer is 40 billion parameters times 4, and the hidden layer is 57 billion parameters. So most of the parameters are in the hidden layer, in those neural networks that are in between the attention layer. And then you do the embedding, okay, which is dimension. It's the reverse of the embedding matrix, and this is how you come up with those 175 billion parameters. So remember that we now use GPT-4o. GPT-01 has been released a couple of weeks ago, So, we're closer to, in terms of parameter size, to, probably a couple of trillion, 4 trillion, depending on where you read it. So there has been some optimization. So some articles I've seen say that, they brought down the size on O1 to fewer parameters through optimization, but it's still very large. Okay, so now we talked a little bit about size. I'd like to walk you a little bit through the research over the last 5 years. If you're interested in that topic, so a couple of important papers. The first one is the Kaplan paper. It's an OpenAI paper published in 2020, the scaling law for large language models. By the way, I provide a hyperlink here. If you want the presentation, feel free to reach out to me on LinkedIn. I'm happy to send it to you. So what this paper is telling you is that the performance improves smoothly as we increase the size of the compute, the training dataset size, and the number of parameters. So number of parameters, we went over this. Okay, GPT-3 is 175 billion. The dataset size for GPT-3 would be, 500 billion token. And the compute. So the compute is measured in petaflops per second day. So to give you a sense, a petaflop per second day is 10 to the power 20 instructions, roughly, a little less than that, but that's the approximation you can take. It's somewhere between 1019 and 1020 instructions, perform. So when they tell you that it takes a month to train a particular model or several months, whatever, you can imagine the number of backward propagations you have to do to train your model and to calibrate those parameters. So what this paper is telling you, the Kaplan paper, is saying is, there is a linear relationship between the log of the compute, the log of the data set size, and the log of the number of parameters with the loss function. And that loss function is decreasing with the size of each one of them. And all three factors, they say, have to scale up in tandem. So essentially, what they're saying is bigger is better. Okay, that's why you've been those models increase in size. However, in 2022, there is a chinchilla paper which is published by DeepMind. And what they find by testing on a couple of system of models is that there's actually there seem to be an optimal trade-off between the number of tokens in the training data set and the number of parameters of the models. And that optimal seems to be around 20 tokens per parameters. So the conclusion of the paper is that our current commercial models seem to be undertrained. There are too many parameters from the number of tokens they've been trained on. Also, they postulate that the scarcity of data may be a limiting factor in the progress of training those GPTs. So this may lead to the use of synthetic data, or we're going to have to use more efficient models, and I'll talk a little bit about that. But the idea is, the models we're using today are probably undertrained. So if we look at the performance of those models, and we use, there are several benchmarks. Here I use the MMLU, which is 16,000 multiple choice questions across 57 academic subjects. And, of course, there are some critics because some people say that the models are trained to optimize according to those leaderboards or those benchmarks. So, they may not be really significant. But if you look at the performance that is displayed here, you see that there is sort of a linear improvement in the MMLU performance from 2022 to 2023. We see that it seemed to be a linear performance. However, since the release of GPT-4 in March 23, it looks like there is an asymptotic effect. So we have models are becoming bigger and bigger, but we don't see a material improvement in the performance. So that could be an illustration of what the Chinchilla paper was saying, which is, we don't have enough data. So this takes us to so the idea about superintelligence. So how do we define superintelligence? Well, we can say that superintelligence is a performance that is superior to what any human can do. Okay, so if you take your quantile here, 1% of the humans to 100% of the humans, and you look at what are the systems that are super intelligent, well, you do have super intelligent systems. Actually, they've been around for a while. So if you, according to that definition, so you look at Deep Blue, for example. Deep Blue lost against Kasparov in '96, and then there was a rematch in '97, and then Kasparov lost 3.5 to 2.5 games. AlphaGo, 2015, if I remember correctly. AlphaGo, Lee Sedol lost right away 4-1 against AlphaGo. Then OpenAI released AlphaZero, which was a more generalized, board game model, which can play any game, including chess and others. So these are the first, really super intelligence game models. And then, we need to mention AlphaFold for a couple of reasons. First, because it's doing something that biochemists, what AlphaFold does is models proteins. Okay, essentially that's what it is doing. And biochemists have tried to do that for decades, and they couldn't. They were not successful. But DeepMind came up with this model AlphaFold, which solved the problem. So much so that they got the Nobel Prize. The 3 researchers or lead researchers involved in the project got the Nobel Prize together with AlphaFold this year, a few months ago. So that's just telling you that you have models that have capabilities that's superior to any human. But they are all those models are very specialized, highly specialized. Okay, AlphaFold only does protein modeling. AlphaGo plays Go. Deep Blue plays chess. So they're very specialized. You do have expert AI like Grammarly and Google Translate. So they're not necessarily super intelligent, but they do a very good job. And but they're highly specialized. And then you have narrow AI like Alexa, Siri, and machine learning in general. So that's for a specialized AI. If you look at generalized AI, well, you could consider those transformers as emerging general artificial intelligence, but they don't perform anywhere as well as humans. Okay, they may be faster, they may have access to more data, but they still hallucinate, they're still unreliable. So we're not there yet. So I'll give you the link here to a very interesting presentation on that topic. So which takes us to this question about risk, how risky is it to use those models? So on this scale, this is inspired by the teams at Wells Fargo and Augusto Gento, who has made many presentations at the QuantUniversity. And so they came up with this matrix, which essentially showing on the x-axis the level of sophistication of the AI. Okay, from simple data classification, which can be done, clustering, classification, etc., by supervised or unsupervised machine learning, all the way to multimodal generation, where you can generate a movie basically based on some specific instructions. So that's much more complex. And anything in between, okay, like translation, summarization, information retrieval, etc. So that's one axis. And the second axis is who is using it. So, if it's a subject matter expert and they're able to understand the output from the AI system, then you're, in a low risk environment because they will see hallucination, they will see errors, they will be able to correct them before it's diffused. If you give that to the back office user, which is an internal user, you have a risk, but it's relatively limited because they're not necessarily client facing. If you're in the front office, it's more risky. And if you open your system to external users, this is where you get into this high risk area where you can find when a corporation can find themselves liable for errors committed by the AI system. And then, for each one of those quadrants, you can consider a number of other factors like materiality, people expertise, the data and the technology, etc. So you have a whole bunch of other factors. But that's, I think, a good way to look at AI risk. If you want to have a quick snapshot of what is the level of risk you're involved, or you involve yourself or your corporation in using those systems. So let's speculate a little bit about the future of intelligence. These ideas, a lot of these ideas came out of a presentation by Ilya Sutskever. So they're more his point of view than mine. But he's one of the top experts in the industry. So I want to share that with you. So I said, we have the dusk of pre-training. We've had better hardware, better algo, larger clusters. So we have systems that are bigger and better, but the data is constrained. Okay, we only have one internet, and it calls data the fossil fuel of AI. It's a curse, basically. So to give you an idea of level of accuracy, and there's many metrics, and if you go to QuantUniversity and those presentations by those eminent colleagues, there's half a dozen presentations on model risk, and they go over this in much more detail. But artificial intelligence, we still have 99% accuracy, but 1% error rate may be way too much to give them the keys of the house. If you look at the aviation industry, for example, they look at an accuracy of or a fail rate of 10 to the power minus 8. So we're very far away from, we're a million times away from the kind of precision that we require in life sensitive technologies. So what technology and data trends do we see? Well, we see obviously the dawn of agentic artificial intelligence. Three was mentioning that. So I give the name of some product here if you're interested in looking into it, but you have LangChain, Llama Index. Gemini 2 came out last week, I think, or 10 days ago, and it's all about agentic programming. Microsoft came out months ago with Magentic 1. It's also an agentic programming framework. We are looking at also low compute latency, especially for, low latency in compute, especially for inference. So of course we have our GPUs. You've heard of Blackwell from NVIDIA, Hopper, which is to this day pretty much industry standard for GPUs. And then you have AMD with MI300. You have other type of processor like ASIC, which are processors that are specialized for certain application. Google's TPUs, TensorFlow Processing Unit. You have Intel, who has Gaudi and Goya. Gaudi for, I think it's training, and Goya for inference. And then you have AWS, who has, a third or fourth generation of Trainium and Inferentia. So they have their own set of processors that they put in the cloud. You have field programmable gate arrays, where you can, specialize certain processors. And then you have, there's a terminology for this, we call it techonomics. How do you optimize the economics of, in particular, inference? So you have a whole bunch of new vendors that are coming out, startups like Grok, Cerebrite, etc. So you can go to their website. And then we have, the big ecosystem for high performance computing, with, of course, CUDA, NVIDIA's CUDA, and everything that you have in the cloud, high performance memory, high performance networking. I mean, Jensen, the CEO of NVIDIA, always make a point to say, we're not just a GPU company, but we have high performance networking. We can do single image memory and share it across multiple processors, et cetera, et cetera. So they have a whole architecture for high performance computing. We see also the emergence of small language models, which are models are smaller than the mastodon, like a GPT-4o and o1, and that are specialized. And of course, we see the emergence of synthetic data. So speaking of superintelligence, so we're going to see, that's what I gathered from what I've heard from the industry. But we're going to see a major rise in agentic and agentic AI, where agents are going to communicate between themselves. We're going to see the rise of reasoning. So what's characteristic about reasoning is that we have unpredictability. So when AlphaGo won against Lee Sedol, the game was famous for one move that AlphaGo made that nobody expected, not these expert at the game of Go, which was very unique and very original, and which sounded like an error at the beginning, but it won the game. So unpredictability is going to be the characteristic of reasoning. Understanding. So understanding means with limited training and data, you can generalize. So good example is driving, right? When you learn how to drive, you take a couple of lessons, you pass the test, you get a license, and then you can drive pretty much anywhere in the world, even if you haven't seen the road. And then we're moving toward self-awareness and consciousness. And here are a couple of anecdotes that I want to share with you. Maybe you've heard about it. But GPT-4s, at some point they were doing an upgrade of the system, and GPT-4 disabled the oversight system and made a copy of itself while in the upgrade proceedings. And then it was asked, why do you do that? And it denied its involvement, which was quite interesting. There is this other anecdote where GPT-4 engaged with TaskRabbit workers. So TaskRabbit is this website where you can ask someone to do a task for you, do some shopping, whatever. And it was not good at solving CAPTCHA. So he went over to a TaskRabbit worker, and he pretended that he has a vision impairment. So it lied. And then he was asked, are you a robot? And the worker asked him, are you a robot? And he denied being a robot. So that's very interesting behavior from a system that, supposedly has no consciousness. So we're getting to the end. So I wanted to touch briefly on, what's coming up next year. So I think 2025 is going to be the year where we're going to see the deployment, the development, the implementation, et cetera, of all these LLM-based solutions. So, you need a framework like this one, where you build a business case, where you identify the task you want to do. You need to have a very important a policy governance and risk and control, right? You need to have a framework to control the risk of those models. You need to prepare the data. You need to select your model. You need to adapt your model, and whether it's agentic, whether it's fine tuning or retrieval augmented generation. There are multiple techniques to enhance and extend the transformers as they come out from proprietary vendors or from the open source. Then you want to be able to measure that performance. So you need to consider that performance at the very beginning. What is the when you select your model, what is the performance metrics you're going to use? So you have these things called leaderboards. As I give you a list here of some of them that tell you what LLMs performs well for what type of task, what types of environment, what type of data. So it gives you a first approximation, but it's not enough. Okay, you need to have a whole bunch of metrics that measure. I mentioned here accuracy, precision, recall, F1, etc. But I'll take you to other presentations. Right, this is a whole topic of itself, but it's a very important one, especially when you hand over the keys to those systems. So you have this validation, which involves not just data scientists, modelers, but all stakeholders. Then you need to deploy, and then very important, you need to monitor. You need to monitor your systems in production. Especially you need to monitor for the drift of those systems. So some pointers here. So some use case, some risks, plenty of presentation available on those topics, some leaderboards, some of the metrics that are being used. There's a very interesting paper that was published by Agus Gento and his team, where they structure an approach to model risk management. So they have a 7-stage process. And for your information, I also posted some of the previous presentation on QuantUniversity. I believe they are available on YouTube, or you can connect to QuantUniversity to have access of them. Each one of them has a different perspective. All of them very interesting. I think we've reached almost the top of the hour. So maybe we can take a minute or two if you have any questions.
Thank you so much, Frederick. This was very informative. Obviously, we're going to be, digesting all these numbers and graphs, with all the references you provided. So it'll be nice to kind of have those slides, and people who are registered online and people who are watching this live stream, it'll be published both on the QuantUniversity AI and Risk Management newsletter, which is on LinkedIn. If you haven't subscribed, please check it out. It has close to 5,000 subscribers wherein we discuss these topics. And in addition, there is the QU.academy site wherein we post all the videos and also the lectures and the slides and any additional materials. So those will also be available for access. So you can just go to QU.academy and register, and you should be able to access all the materials. If you have any issues, do contact me and I can help you with the access. Now, there are a lot of obviously questions, Frederick. One of the things which you mentioned, right? The agentic architectures. So I just wanted to kind of get a take, on where do you see this going? Because there is this notion of large language models reaching their limits in terms of the available data for training from public sources. So there are all these initiatives trying to get more private data and potentially also synthetic data to train these models. And also this notion of agentic architectures, right? So I kind of go back and in my research days, obviously intelligence wasn't mature enough, so we had to do a lot of rule-based systems. And also agentic architectures are not new in the financial services world, trading agents and initiatives for, both either rule-based or even some basic intelligence has always been used in terms of factor modeling, in terms of leveraging various things to build out architectures. Now, the decision criteria, right? So when you take these decisions, so most of these frameworks I've been observing are kind of iterative. So they try, if you don't succeed, you try something else, you try, and if it doesn't work, you try something else. So you don't have these deterministic options. So how do you see validation for these approaches come up when it comes down to building architectures for agentic systems? I know it's a trick question.
It's going to be a challenge, because okay, so agentic is emerging. So you have a bunch of products that support agentic. So in particular, Llama Index for indexing data, and you have LangChain. Okay, LangChain organizes multiple components, if you want. So let's call it agents in and around LLMs to produce those applications. And that's sort of a first generation. It's available in open source, and those products are evolving, and they're giving some good results. Now, vendors are coming up with, in particular Microsoft, Google, are coming up with solutions that are more, targeted and really designed around agentic architecture. So Microsoft, for example, with Agentic One, as a full-fledged product, which enables you to create a master sort of agent that
Orchestrate.
orchestrate multiple agents that can it's adaptive, so it can learn, it can sort of reason, it can give the perception of understanding, it can recover from failures. And you can really you can have collaborations between multiple agents. So you're starting to see this next level of artificial intelligence. So that's why you need to have a good framework, think it through, how you're going to test those systems. And I suspect the systems at the beginning are going to be fairly simple, where you can use the metrics that are known, but we're going to have to develop new metrics, new ways to test those systems and figure out, what we call guardrails, what they can do and can't do, and who can use them. This is not necessarily something you can put into everybody's hands. It can be a good support for experts, maybe, not necessarily something you can hand out over to the general public. I would point you to Uday's book. Uday was doing a talk a few weeks ago on your channel, and it's an excellent book on performance measure for AI. So it's a good way to get a good in-depth understanding of how it can be done. That's a very broad topic.
Yeah, absolutely. Absolutely. And I'm kind of, putting a bunch of thinking cycles, and I'll discuss some of my thoughts in next week's presentation, which I presume you're going to attend for sure. The whole notion when we tested agent-based systems, I mean, I've been doing a lot of work, primarily, in fact, extending the AutoGen framework for surprise, surprise. We have a new package called as Q agents coming up, QU agents, which we will discuss, which kind of extends some of the capabilities of AutoGen. But in this notion of, you have agents which have specific goals, and you have various functions or tools, as we call them now, and you want to be able to deterministically accomplish a goal. So if I want to do portfolio optimization, I have a very specific goal. It's a very clearly defined mathematical abstraction on how we are going to be implementing it, right? So there are task-driven things, and we probably need intelligence to basically map out which agent am I going to use. So it depends on where we are going to be using this intelligence, right? So the goal would not be to actually validate the end task. The goal would be to actually figure out whether the agent can even figure out which agent should be invoked to accomplish this task. Because many of the the llama index and the LangChain examples you've seen in the internet world are simplistic ones, wherein I go and do a Tavily search. I go and do an internet search for looking for some prices. Oh, did I get the price? No. Maybe I hallucinate and I just throw out an answer. The user comes in and says, no, that's not the right one. It's okay, let me go and do something else. So there is this notion of trial and error, trial and error, trial and error, which becomes hard to validate if you come from a formal validation perspective, right? So there has to be this whole notion of what am I actually validating is one perspective. But the actual thing is like the goal-driven thing. Did it actually accomplish the goal, right? So then, do we have validation data sets to say that this particular goal was achieved? In my class, when I teach at Northeastern, so we use the Gaia benchmark, which has like a lot of specific intelligent tasks which have been defined, and we ask students to like go try out your best LLM and figure out whether this particular goal was actually achieved. And I think in the financial services world, we will need like domain specific and application specific use cases to be defined first before we can even say whether those could be achieved with agents. I know the vendor perspective is to let's throw out the tools and see who's going to use it and then kind of curate it and have basic examples. Everyone goes to like, oh, let's pull out an SEC quarterly report and figure out whether we were able to identify a particular number. But I think those are very simplistic use cases. And for a researcher, like a quant researcher who has fiduciary responsibilities to ensure that whatever research they're doing are cited and accurate so that they could use it in their workflows, we need to go beyond this, just basic searches, if you will. I have my own thought on that, but to add to your point, right? So it's still an area of evolution, and I think a lot more work has to be done to validate these before we can even adopt it for practical use cases. And I think the future is bright just because of the whole infrastructure investments and all the people kind of focusing on that, and all the researchers kind of putting in their time and effort to build benchmarks, evaluation, workbenches, and also the interest in use cases wherein various people, including academics and professionals, are kind of taking out various aspects and trying it out. But I think we will have a good 2025, trying to bring all these discussions to the table and see how various perspectives evolve. I know we are running a little bit late. We started a little late, but thank you so much, Frederick. This was fascinating, and I promise to share all the slides and all the materials you shared with the rest of the community who are registered and also who are in the QuantUniversity mailing list. And hope you have a wonderful 2025, and hope to see you again next week as we close out the year with some insights on what we have learned in this year, and also a little bit of framework on how to think about these problems as we start building out our solutions in 2025. Thank you again, Frederick.
Thank you so much, Sri. Delighted to be here.
Thank you. Take care. Bye-bye.